Hi, everybody. This is Mr. Folly, woo, and welcome to 3.2, where we are going to talk quite a little bit about shapes. Okay, so this one is a 3D tough thinking one, so let's get ready to that. All right, so 3.2. Shapes, single bonds, double bonds, triple bonds, Lewis dot. Bonding makes substances more stable. We talked about that last time. Energy is released when bonds form. That means more stable. Remember, high energy is unstable. Energy is absorbed when bonds break. Again, we've seen it before. We'll hear it again. We've got BARF. Breaking, bonds, absorbs, energy, releasing, energy, forms, bonds. Hey, another podcast, another BARF. Okay. So delta H is negative when bonds form. Delta H is positive. Oops. Delta H is positive. Delta H is positive when bonds break. Forming bonds is favored. Again, that's going to be more stable. Okay. Covalent bonding comes in three flavors: single, double, and triple. Okay, so that's not all that crazy to deal with, okay? So my single bond is going to be the longest, it's going to be the weakest, there's 2 electrons involved. This one might surprise you. Long is weak, okay? So that is true, all right? So if I were to try and break a stick over my leg and the stick is this long, and I put my little hands on here, and I put my little hands on here, and I break it over my knee right here, that's pretty easy. But the shorter the stick is, the harder it is. I'll show you that in class. It works a little better in person. Double bond is middle length. Whoops. Double bond is middle length, middle strength, 4 electrons in bond, so double bond uses twice as many. Triple bond is the shortest, strongest, 6 electrons involved. Remember how bonds share a pair of electrons. So remember, bond energy equals Q1, Q2 over radius squared, and triple bonds are shorter and stronger. Or triple bonds are stronger, so they're shorter. So remember, the charges would be the same for each one because we're just talking about the charges on the nucleus. So some atoms, so for example, if I'm looking at a carbon-to-carbon bond, a carbon, double carbon bond, and a carbon, I didn't mean to make my C smaller, but I did mean to make the distances shorter. So, all right, structural formulas show the attachment of atoms. Okay, so structural formulas show the attachment of atoms. CO2 is not COO. We need to find out how to get the correct arrangement. Lewis dot structures give you the correct arrangements. Okay, so I want to put a little star on here. I found a way to do Lewis dot structures that's different than any other way that I've seen before. So my way is a little bit different, and I really think it's better, and I really think I should be selling it to the entire world. But in either case, this is what we get. To draw a correct Lewis dot structure, put the least frequently occurring atom in the middle, or C. Carbon always goes in the middle. Arrange other atoms around the middle atom. So note, we will have one central atom. Put valence electrons around all the atoms, aiming single electrons at each other. Now, I'm going to admit I often put Lewis dot structures in as I go. Okay, so when we do valence electrons, we look at the periodic table, and here's my cheap little periodic table. We've done this before. 1, 2. Honestly, this only is good for nonmetals. So if I'm in this column, so like, why does boron have 3? Well, boron's in the 3rd column. Why does carbon have 4? Well, carbon's in the 4th column, and so on, okay? So once we put the dots around it, then we're going to sing, connect the dots, la, 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 and you are allowed to form double or triple bonds. By the way, I love one double. That's kind of what I look for in the world, and it just kind of makes me happy, and in AP chemistry, you'll see why that happens. Outer atoms must have 8, except hydrogen has 2. Oh, here are my exceptions. Hydrogen has 2. No. Aluminum and boron have 6. No. So many exceptions. Okay. The central atom prefers to have 8, but if and only if is on the 3rd period or below, it can have 8, 10, or 12. 10 and 12 are not preferred, but they're acceptable. So I look at them like emergency exits. Okay, so our emergency exits jump out of the window of the 2nd story building and land on a bush and then run. Okay, I've never done that in my life, nor do I ever look forward to that. But if there's a problem in the school, it's on fire, we got to get out of here. We got to go out the emergency exit, and we have to do that. So we want to obey the octet rule. We want to go out our regular door. But if it's on the third row or below, so I'm going to focus in on this part over here. So this is nitrogen, oxygen, fluorine. Below nitrogen is phosphorus, sulfur, chlorine, okay? These guys right here cannot do it. No. For our class, they're just simply not big enough. These guys can do it. Yes, they are big enough. They can break it. Yes, I can. Okay? So it's kind of like being able to dunk a basketball. Either you can or you can't. All right? You are the master of the electron. You can pick one off of one atom and put it on another. You can form double and triple bonds. You can get rid of single electrons. Now, that's the most important thing. You cannot have single electrons. Okay? If something is an ion, so for example, if I have NH4 positive, pretty common ion. A positive ion means you're going to take away an electron. A negative ion means you're going to add an electron. Now, this is anywhere you want to. This loose dot structure looks like garbage. Hey, guess what? I get to take one away. Oh, hey, guess what? I get to add one. Now, remember, take away for positive, add it for negative. Charge of 2 or 3 means you add 2 or you add 3 or whatever it is. So let's do some examples. Got H2O here. So what goes in the middle? Oxygen is the least frequently occurring atom. Oxygen's in the 6th group of the periodic table. I have 2 H's. I'm going to aim them at my single electrons. So again, much slower. Central atom is oxygen, least frequently occurring. 6 valence electrons, because it's in the 6th column on the periodic table. 1, 2, so 1, 2, 3, 4, 5, 6. It didn't really matter where I put them. It should be north, south, east, and west, top, bottom, left, and right. It didn't matter where you put them, but wherever you put your single electrons, that's where bonds are going to form. That's why I really like focusing on putting this on here first. Hydrogen has 1 valence electron. I aim my my singles at each other, and I sing, connect the dots, la, 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 connect the dots, la, la. I have no singles. I won, okay? I have 8, and I have 2. 8 for oxygen, 2 for hydrogen. I'm a winner, okay? Take a look at NH3. Nitrogen, there's only 1 nitrogen, goes in the middle. 1, 2, 3, 4, 5. It didn't matter where I put the pair. I don't know. I put my pairs on top, I guess. Hydrogen, I have 3 of them. I aim them at my single electrons. 1 hydrogen, 2 hydrogen, 3 hydrogen. Hydrogen, again, has 1 valence electron. I aim it. What if I made a mistake here? And I put my hydrogen aimed the wrong way. What am I going to do? I'm going to sing, connect the dots, la, 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 connect the woo. Okay, now that looks dumb. So what would I have to do? Clean it up. That's okay. La, la. Beautiful, 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 beautiful. CO2. Carbon goes in the middle because carbon always goes in the middle. It is also the least frequently occurring. Okay. All right. Whoops. And now notice how I put my oxygens a little bit differently. I have 6 valence electrons, but I'm going to aim my single electrons at my central atom because I know that's where the bond's going to happen. I connect the dots. La, la, la. Uh-oh. Still connecting dots. La, la, la. So see how I made a double bond there? I'm going to erase it and make it be a prettier double bond. Connecting dots foolishly. Okay, that's an ugly double bond, but it's still another double bond, right? So if I have a double bond, let me just make these 2 bonds look a little better. Remember how we want to look and see if we've got 8 for all of our big dogs. So let me show you how we get 8. So I'm going to start with carbon. Carbon has 2. Oh, no, I thought that'd be darker. Carbon has 2, 4, 6, 8 from those bonds. Does that make sense? So there's 2 electrons in each of those bonds. Carbon has 8. Carbon is good. Let me talk about oxygen. 2, 4, 6, 8. Now I can double count those bonds, okay? So they're good for oxygen, they're good for carbon, they can share them. So that means oxygen's 8 and this one's the same as the other one, okay? So that means you shouldn't leave your counting on here, but there you go. So this is a good structure. I'm a winner, I'm a winner, I'm a winner. CO3 negative 2. Oh, doggies, it gets a little bit harder. Whoops. CO3 negative 2. Actually, you know what? I'm going to delete this guy right here because it shouldn't be here. Oops. Ah, look at that. I bet this will mess up my whole screen. Okay, so CO3 negative 2, I'll just erase and use my space here again. CO3 negative 2. Carbon's going to go in the middle because carbon always goes in the middle. But this time, I'm going to have 3 oxygens around it. 1, 2, 3, 4. Oxygen, oxygen, oxygen. Didn't matter where you put it, but it's got to be kind of aiming at carbon. 6 electrons for oxygen. Connect the dots. La, la, la. Okay, see a double bond. I see a double bond. Oops. Okay, so now this one is tricky. All right, I'm going to make my double bond look prettier here. Okay, now the single electrons that I have left, I notice a single electron here and a single electron here. I may be tempted foolishly to connect those dots. That would form a ring, okay? So somewhere up there, I hope I wrote rings are wrong. Oops, right here. Rings are wrong. So let me show you what I mean by a ring. What I might have thought for half a second is if remember, I mastered the electron, so I'm making this become a little more obvious for us. All I did was change places. This right here would be a ring, a triangle ring, but it's a ring, okay? That's not allowed, okay? So, but I do have single electrons. The number one rule of Lewis dot structures, you cannot have single electrons, okay? So I remembered, oh yeah, this is negative 2 charge. Negative 2 means add 2 electrons anywhere that I want to. Well, hey, I'll change this. Here's 1, here's 2. That takes care of all of my single electrons. So we can check for our octets, which means make sure everything's got 8 again. So here we go. For carbon, 2, 4, 6, 8. That's good. Carbon's good. For, I guess let's change color. For this oxygen, 2, 4, 6, 8. This is the same, right? This guy's the same as the other blue one. And then, oops, I keep going to the wrong one. For this one, I have 2, 4, 6, 8. So everybody's got 8. So this is a happy, happy one. All right. Let's do pickle 5. PCl5. When your friends and neighbors are doing this stuff, they will talk about counting valence electrons and how annoying it gets. If you stick with this, you will not have a problem. PCl5, chlorine. Remember, there's one central atom. So I start off with north, south, east, and west, and then I have to pick somewhere to put the other one. I'm going to put it in northeast. Chlorine from the periodic table has 7 valence electrons. Oh my goodness gracious, that's a lot. So I'm giving them all 7, and notice how I'm aiming my single electron at my central atom, because remember, we all have to bond to the middle ones. That is mama atom in the middle. Central atom, center of my world. Connect the dots, la, 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 connect the dots. Oh no. See how I made that look ugly? I'm going to, remember, I'm the master of the electron. Now you might go, oh no, phosphorus has 2, 4, 6, 8, 10. No! But remember, everything's got to attach to the central atom, so that seems like it might be okay if phosphorus is on the 3rd row or below. Right? Phosphorus is number 15 on the periodic table. It is on the 3rd row, and it can break the octet rule. And you know what? In this case, it has to, right? Why does it have to? Because I used an ugly orange highlighter. Why does it have to? Because I need to bond 5 atoms. 5 times 2 is 10. So that one's okay. And we're good. If this seems like a lot, that's because it's the introduction. We're going to do a whole bunch of them in class. Let's do our old friend ASF5. What goes in the middle? Least frequently occurring one, arsenic, AS. Arsenic has 5 valence electrons, F. Does arsenic have 5 valence electrons? Let me find a little periodic table here. Arsenic has 5 valence electrons. Uh-oh, I think I might have a mistake on here. So it's ASF5 positive. So I have in the back of my head, that I get to remove an electron whenever I want to. I forgot to keep drawing my F's. And again, I like to put my extra 5th one top right. It doesn't really matter, but it's okay. Boom, 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 boom. Oh no, this is ASF5 positive? I'm checking again to make sure AS is not in the 6th column. Bum, 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 bum. Ooh. This is supposed to be ASF5 positive, and you know what? This is me grabbing a bad one. This one does not work. I apologize so much for that. So for that, I will say, oopsie. I don't think that such a little doggy exists there. So I'm going to say that one wasn't supposed to be there. As soon as I looked at it, and you saw me check it 6 times, I'm like, oh no. But that is it. So how do we do Lewis dot structures? Valence electron, least frequently occurring one goes in first. Valence electrons, connect the dots, la, 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 and then put a smile on our faces. Toodles.